Welcome everyone for this webinar series. Today we are extremely lucky, fortunate to have Professor Sheng from the Hong Kong University of Science and Technology. And Professor Sheng, as you know, is extremely famous in the field of condensed matter theory. And he will talk today on conceptually based design of ultra-broadband microwave metamaterial absorber. Professor Sheng.
Thank you, Sebastian, for arranging this talk. Now, my previous works are mostly in the acoustics, and there is a reason for me doing this microwave absorber, which I will get to as soon as I acknowledge my collaborators. And they are my two students. And on the right, his name is Sicao Qu. He's mostly theorist. On the left is Yuxiao Hou. I think both of them are in the audience. They're mostly experimentalist. Okay, what's the motivation? The motivation is actually the upcoming 5G. And we all know 5G is much faster and with much more information carrying capacity. And they can do that because 5G uses many high-frequency microwave bands. And we all know that microwave power is a quadratic function of the frequency. And furthermore, there will be 5 to 10 times increase in the 5G communication base stations in those regions where you have 5G. And so this work is targeting the frequency range of 3 to 40 gigahertz, the regime where most of the microwave power resides. And that's our target absorption band. So what's the motivation? Motivation is that, at least I believe, that microwave absorbers can play a role in providing a balance between monitoring and privacy, as well as in remediating the health concerns due to long-term exposure to at least one order of magnitude higher microwave power, at least in the 5G active space, where you have these microwave permeating the space. You know, exposed for a few minutes, it doesn't matter, but if day in and day out, you have order of magnitude more microwave power, that's a concern. And we know microwave does interact with human cells. So of course, nobody has conclusive evidence that it will do damage, but it is nevertheless a concern with order of magnitude increase in power. And another motivating point is that we want to achieve the electromagnetic optimal absorber as what we have done in the few years past in acoustics. So that's another target. So let's see whether we can do that. So let me first say the underpinning conceptual elements. In fact, this first paragraph summarizes the most important part. Essentially, we use a very simple structure, which is a metallic ring. And when we say metallic ring, it brings to mind the famous, like the splitting ring resonator by John Pendry and collaborators, and so on. But here, we will have a different type of resonances at the higher frequencies. And put in the presence of metallic boundary will ensure a large resonance line width due to the radiation loss, as well as it's going to generate large magnetic permeability arising from dipole resonance interaction with this image resonance. This, in fact, I will spend probably at least 1/3 of the talk in clarifying what I'm saying in this paragraph. Once we have that, then the next is to use something called dispersion engineering by tuning the dissipative resistance to achieve broadband absorption condition. And then we are going to use self-similar hierarchical structure to extend the absorption spectrum to the ultra-broadband regime. And then the absorption of the diffraction orders, because once you have the ultra-broadband regime, diffraction definitely kicks in, and you want to absorb these diffraction orders before they get out of the sample. So, and we use the conventional foam patches in that regard. So the first thing we want to know in the microwave absorption is the impedance. The impedance is defined by square root of the relative magnetic permeability divided by the relative Dalish constant, mu over epsilon, square root. And because at microwave frequencies, almost all the materials exhibit magnetic permeability close to 1, and while the Dalish constant can be large, for example, in the metal, therefore, usually the electromagnetic impedance can be small, and therefore it mismatched with that of vacuum. And as a result, most of the microwave will reflect it at the interface before it can be absorbed. And so at least our aim is to obtain a high impedance, namely we have a high magnetic permeability as a precondition. And we want to use a metallic loop, as I mentioned before, and with high frequencies can induce an electric dipole resonance. And we enhance this trend by using a periodic structure where the separation between the metallic rings acts as capacitor that couples the neighboring resonances, and that enhances this, this trend. And finally, with the interaction with the image resonance, while the presence of a metallic backing can lead to a large magnetic permeability, and I will explain how. So now let me share a screen of something that's hand-drawn. Can you see this? I have just drawn with my hand. So when we talk about metallic ring, usually the image that comes to mind is that of the Faraday law, where you have a current around the loop. But I propose that at the certain frequencies, that with the electric field pointed in a direction as drawn, you can regard the metallic loop as composed of two metallic segments together. And if the length of each segment, W1 plus H1 expressed here, is equal to half the wavelength of that relevant frequency, then we can have a half wavelength electric dipole resonance, okay? So that's quite simple. And in this regard, I also want to mention that if we can have half wavelengths opposite current, then we can have magnetic dipole resonance, okay, in this regard. Okay, now let me come back to the PPT. Okay, so what am I talking about? So let me focus on the figure A. So that's the simulation setup. That's the unit cell in which we have on each of the four sides half of the metallic ring, and they are separated from its neighbor by a gap about 8 millimeters. And the width of the metallic ring is like 16 millimeters, and the height of the ring is like 8.3 millimeters. And so the half wavelength condition basically is given in this formula, C divided by 2 times W1 plus H1. Now, in figure B, we have shown that at simulation shows at 6.3 gigahertz, there is a near total reflection, near zero transmission, and a little bit of absorption. And we can verify that's a dipole resonance by comparing the frequency at which the total reflection occurs with the formula given on the right-hand side. So that's shown in C. And you can see the agreement is very good. And in D, you can see the dipole resonance, of course, is going to radiate. So this is obtained by subtracting off the incident wave. And you can see the dipole radiation. And that accounts for the broad sort of the resonance peak because it's lossy. And on the right top, you can see the capacitive effect. Once you have the dipole resonance, so you can have a coupling between the neighboring ones. So essentially, we have a two-dimensional array in the checkerboard geometry. And obviously, this checkerboard geometry is purposely made to make the absorption independent of the polarization. Okay. Of course, at the normal incidence, the two polarizations are same. But you will see, to a large degree, even at the oblique incidence, it is pretty well holds up. Okay, so next, we are going to extract the effective magnetic permeability and effective Dodge constant of this structure. This is done by copying the technique we found in the literature, because now we are going to put a PEC backing to the two-dimensional checkerboard structure. This PEC structure is separated from the checkerboard structure by about 6 millimeters. And in order to have some transmission, we follow the technique in the literature. You have some kind of holes, 4 holes drilled on the corner, so that as to obtain the transmission. And in this way, I'm not going to go into details. We can obtain the reflection transmission. From that, we have the effective parameters extracted, namely epsilon effective and mu effective. And what we want is this effective impedance can match that of the vacuum, and then the thickness of the sample, K times D, multiplied by the imaginary part of the effective parameters, is just enough to do the job of absorption. Namely, you cannot absorb anything if you don't have anything, right? If it's a too thin, then you cannot do anything. Okay, so let's see what happens when we have this electric dipole resonance when it's backed by a PEC boundary. Now, this is just a comment that the condition on top cannot be satisfied for all frequency due to the causality constraint, namely the Kramer's chronic. But we want to make it as broad as possible, of course. So this is what happens, okay? So So what happens is that when we add a metallic boundary at the bottom, it appears to have a creation of two high impedance resonances at 3.38 gigahertz and 8.02 gigahertz. And this is apparently due to the interaction of the electric dipole resonance with its image resonance. And I'm going to show you how in the next view graph. Okay, so just accept that for the time being. And you can see that in the middle, around 5.3 gigahertz, the real part impedance essentially goes to 0. So that is a PEC essentially, okay? So at 3.38, 5.3, and 8.0 gigahertz, all have almost total reflection, okay? But at 3.38 and 8 gigahertz, the total reflection is really caused by the PMC boundary condition at the top plane of our sample. So we are showing this view graph for the 3.38. You can see lambda over 4, where we have from the minimum to the minimum, which is just on the top of that. Essentially, when you have a lambda over 4, you have a minimum to a maximum. So at the top plane of the sample, you have a maximum in the tangential electric field, and that's the PMC. For 5.3, on the other hand, you have lambda over 2, and that means you have a PEC. You have a minimum, or the 0 of the tangential electric field. At 8.02, it's the same thing, is quarter of wavelengths. And moreover, we can extract more information from that. Namely, we know from the PEC at the bottom to the top plane of the sample, the distance is 14.2 millimeters. Okay, so at a PEC, tangential electric field must be 0. And at the top plane, it must be for 3.38, it must be a maximum. So that means the effective wavelength must be a quarter of a wavelength equal to 14.2 millimeters at 3.38. And from that, we can deduce that the effective index refraction at 3.38 is around 1.6. Okay, I just want to mention that. And the same thing for 8.02, we can deduce the effective index refraction is around 2. Okay, so that's the information we extract. And so the electric resonance is essentially the magnetic anti-resonance and vice versa, okay, here. And the PMC effect, so that's what I've already told you about, the PEC effect. That's I already mentioned. So let me explain how this two high impedance resonance occurs. And high impedance means large magnetic permeability, as I mentioned in the beginning. Okay, so here we have a metallic ring, okay? And the current flow is as shown by the red arrows, okay? And now we put a PEC backing, okay? And the distance from the top of the sample plane to the PEC backing is the lowercase d. And now on the right-hand side, we show the image plane or the symmetry plane. And in the low frequency or the static limit, this is the what we expect. Namely, the current is reversed, okay? And what I want to draw your attention to is the red dashed box, okay? I want to focus only on the original J1 and the image J2, okay? Why is that? And the big distance d here is 28 0.4, namely twice of the small d. Because at high frequencies, we have to consider the retardation effect, of course. So what I've drawn for you, of course, is essentially the static or the low frequency limit behavior. But at high frequencies, the retardation means we have to take into account the phase. Essentially, the current flow on the top, J1, is going to send out a signal through the vector potential, and is going to travel via the speed of light to the bottom, essentially to the image, to the J2. And we have to take into account the effective index refraction, and the signal better be that just in phase when it gets to the J2 as the signal sent out from J2, so that they reinforce each other. And in that sense, we have a pi difference between the J1 and J2, and that implies a magnetic dipole resonance. Okay, and here we have taken into account the index refraction of 1.6 and 2, as I mentioned before, and exactly for the first magnetic high impedance resonance, the phase difference with the J1 and J2 is exactly pi. And the second one at 8.02 is exactly 3 pi. So it shows it is really a magnetic dipole resonance. And that's why you have a very high magnetic impedance, high impedance or magnetic permeability. So now, in A, in the vertical axis, we show with the red solid line the real part of the impedance normalized by the vacuum impedance. And this is what we have seen before. So at 3 point something and 8.0, you have high impedance. And that's the raw material we have been looking for. These are the high magnetic permeability we want. And now what we want to do is to spread these high magnetic permeability between the two magnetic resonances so they can achieve impedance matching. And how do we do that? We just put some chip resistors, okay, at the bottom of the metallic ring. Put 2 of them symmetrically, okay, on the bottom. And the total resistance is 440 ohms, which is 16% higher than the vacuum impedance. Essentially, it's actually the value is not that sensitive, but we just try to optimize this. Okay, so it's close to the vacuum impedance, and as you can see, the over the region of frequency that's between the two magnetic resonances, the impedance is nearly 1, namely we have achieved almost impedance matching. And moreover, the imaginary part is small but non-zero and just enough to absorb all the energies. And so let's see a picture of the Poynting vector of this structure, see how the absorption occurs. So we plot from 4 gigahertz to 8 gigahertz, and in fact, they are very similar, you can see. And over here, you can see the arrows indicate the Poynting vectors. And the color indicate the local impedance value. Red and dark red means high, okay, and greenish is 1 and things like that. So you can see on the surface, you have inhomogeneous impedance, but the average is close to 1. That's what's important. We are talking about in average. And you can see the power goes through the capacitive gap, okay? And then it turns around and get dissipated in the resistor from the bottom. It turns around. And so, as I already said, the average impedance on the top is very close to the vacuum impedance. Okay, so now we have this thing. Let's say how well these structures perform. Okay, so also the ideas comes into our mind. If this performs well, why not have a smaller structure so as to extend the performance to higher frequencies? So essentially, you can create a self-similar structure, okay, with a smaller metallic ring. And so we essentially have a smaller metallic ring, actually 1/4 of the original size. And these are the actual experiment and the simulations. So for the large metallic ring, a layer of that, the absorption is 99% from 3 to 9.5 gigahertz. Essentially, this band is defined, as you remember, by the separation between the two magnetic resonances, high impedance resonances. And for the smaller ring array, the absorption is from 10 to 36 gigahertz, is not as high as 99%, but is greater than 95%. So it's not bad. So the idea is to splice these two absorption bands together so as to achieve a ultra-broadband absorber, okay? And we have tried the various ways. Namely, we tried like the smaller ring is being 1/3 or 1/4 or 1/5. And the 1/3 is not so good at the higher frequencies. You can see that. The red line means the combined, and it doesn't do so well at the high frequencies. The 1/5 is pretty good at high frequencies, but it does not so well at lower frequencies. So as a compromise, a quarter is the best choice. Is a compromise. It drops down, as you can see, between 35 and 40 gigahertz, but we are going to take care of that by using the conventional foam absorber, because we know that's the that's extremely good at higher frequencies. So 1/4 is the optimal value for us in this case. And so this is the structure. You can see that, okay? Very simple. These metallic rings are printed on the PCB, okay? Printed circuit boards. So they are extremely cheap and can be made very accurately. And so we cut slots into the stripes and assemble them into checkerboard the layers, and one on top of the other. Of course, these two metallic rings cannot be right on top of each other, because if they do, they are going to interfere with each other. So some separation needs to be. So there is some kind of a design optimization, okay? We don't want them to interfere each other too much. And this is the actual large ring shown, the sample. You can see, probably you can see the gaps. That's where we put the chip resistors. And so they can be mass produced very easily, okay? And together with the two-layer structure, diffraction definitely kicks in, okay? Because it is inevitable when you have a high ultra-broadband regime, because at a high frequency regime, the large rings is going to diffract. And diffraction order increases with increasing frequency. In fact, for our structure, we can identify on the order of 170 diffraction orders because the diffraction is two-dimensional. So you have two indices, and there are many, many diffraction orders at high frequencies. And later on, I'm going to show you the energy of the diffract orders. Of course, that's done by using COMSOL simulation, because measuring them experimentally will be difficult. So I'm not going to go into details on how what is diffraction and so on, and I assume this is well known. For long wavelengths diffraction, you have a large diffraction angle, but you also have longer decay lengths. They are harder to take care of. But fortunately, at the long wavelengths, the diffracted energy is not that big. For the shorter wavelengths, you have many more diffracted energy, but they are easier to be absorbed by a dissipated medium. So what we do is we absorb these diffracted orders by using conventional microwave absorbing foam. Because you notice in our structure, we have a checkerboard structure, and there are a lot of empty spaces in between. So on the top layer, we can put in the foam patches. We are not going to waste this space. So we put in the foam patches, and they perform extremely well, okay? So they absorb all the diffracted energies, okay, and inside the sample. So you can see this is the large ring array. We assemble them, and this is small ring array assembled. And this is one on top of the other. Of course, we leave some space in the PCB board so that the metallic rings don't touch each other. That's adjusted. And then we put 9 millimeters of the conventional microwave absorbing foam in the interstitial spaces. So we don't waste this kind of space, okay? And then this is the overall picture of the sample when it's completely assembled. It's 22 centimeters by 22 centimeters, and they can be measured. And now let me show you the measurement system. This is nothing special. This is the darkroom. It took my students, Yu Xiaohou, quite a lot of effort to put together this. In fact, it's a movable darkroom. It's a network analyzer, of course, and horn antenna, so that's nothing special. And this is the performance at a normal incidence. So we have nearly achieved what we set out to do for the acoustics. This almost looks like the acoustics absorber, okay? And because we used the conventional microwave absorbing foam, so we are obligated to compare our absorber performance with that of the conventional foam, which is shown here by the green triangles. And fortunately, in the comparison, our absorber is still better than conventional foam. Otherwise, there's no point, right? Okay. But the reality is the performance of conventional foam is really quite nice, quite good, okay? Amazingly good, especially in the high frequency regime, okay? So we don't need any metamaterial absorber for microwave at a high frequency regime. The conventional form can do it extremely well, okay? But we are still doing better at the low frequency regime, okay? Mostly in the low frequency regime. And for the oblique incidence performance, we have to distinguish the T and TM polarization. And so what I'm going to show you the averaged behavior. On the top is the 22.5 angle. The bottom is the 45 angle. Both are without foam. Without foam is already pretty good. It's mostly above 90%. But to the right here, we add the foam patches, and it becomes extremely good. Okay. And so the measurement can only be done up to 45 degrees. So what we want to do is to show you in the dB scale. And you can see in the dB scale, at the 45 and 22, at the 45 degrees, the top one is without the foam, bottom one is with the foam. The with the foam is actually only slightly worse at the 45 degree than the normal instance. It's polarization, quite polarization insensitive, and is ultra-broadband. And and here I show you the diffraction energies, okay? So on the top, we show you that at the normal instance, without the foam, you can see the fraction of the incident energy that's diffracted at a higher frequency range can be more than 50%, okay? It goes from low frequencies from 0 to 10% and up to 50%. Now, if we add the foam, you can see the most of this diffract energy is absorbed by the foam. The same thing at the 45 degree incidence. That's shown at the bottom. So you asked, what happens to these that escapes? Okay, well, when they escape, it cannot be detected by the source. It doesn't go back to the source. Of course, it's deflected from the target, so it's going to be absorbed by the environment. Okay, probably 1 or 2 bounces. It'll be totally absorbed. So the simulation shows diffraction energy is mostly turned into absorption, both for normal and oblique incidence. And so here we show you the oblique incidence up to 60 degrees. 60 degrees. So I'm not going to dwell on this, but you can see at 60 degrees for TE polarization at the low frequencies, it can be poor. Can drop down to something like 60%. But the high frequency is still good with the foam. Without the foam is not so good. But the TM is pretty good. So even up to 60 degrees is not too bad. So let's summarize. So our design essentially can satisfy the 4 challenges, namely the operating bandwidth is fairly broad, 3 to 40 gigahertz. And the simplicity of geometry is basically single resistor ring. The cost of fabrication is extremely cheap, a PCB, okay. And thickness absorption trade-off, and that's what I'm going to show you. This is the causality limit, which is defined by an integral of the log of absolute value of the reflection coefficient. And in this, by using this causality limit, our sample thickness is only 5% thicker than the minimum thickness dictated by the causality. So it's not bad. Okay, I think ours is the closest. So how about comparison with some of the competitive absorbers we can find in the previous literature? So to do that, we want to define two indices. One is the relative bandwidth. That dimensionless parameter upper limit is 2. Okay, it cannot be greater than 2. So as close you get to 2, the better. Okay. The other parameter is the causality ratio, namely the sample thickness divided by the causality limit, and you want that as close to 1 as possible. So here is a table, and we lift out all these numbers from the published values when they are available in a paper. And so you can see that in terms of the combined relative bandwidth, ours is 1.72. In fact, our sample, I think, can really absorb very well beyond 40 gigahertz, but our measurement system can only measure up to 40. Why we believe that? Because we have foam, and the foam can absorb extremely well, up to 70 or something, 90 hertz. Nothing to stop that. But we want to stop it at 40 because that's the limiting frequency of our instrument. And it's 1.72 is not too bad. It's very close to 2. And the RC is 1.05 compared with the others. And you can see it's not too bad. That's all I can say. So the prospect is that current stage, and we have verified the performance both numerically and experimentally, and further development may focus on optimizing the fabrication process and reducing the cost. And we see the potential application in the privacy protection, health concern remediation, and even energy harvesting or sensor. Why do I say that? Because by using a metallic ring, we have currents. And when we have currents, we can do something with sensing or energy harvesting. Okay. For example, it's very difficult to energy harvest from the microwave foam. Okay. But by using a metallic ring, we have currents. And once you have currents, you can do something like that. Okay. Yeah, you can have a sensor and things like that. Okay, so that's all I have, and I leave a few minutes. It's almost 10 here for any questions and suggestions. Thank you.
Thank you very much, Professor Sheng. It was a talk. So I welcome any questions from the audience.